go. Excellent. Hi, my name is David Venables. I'm the CEO of Laverock Therapeutics, and it's my pleasure to introduce you to what I think is a really exciting platform that we're developing for the development of programmable or the use of programmable gene silencing to transform advanced therapies. So after more than 25 years in this sector, then I've seen obviously lots of different trends, different things come and go, different technologies that have been used and developed, but I can say that this is one of the ones that I'm really excited about because it offers a totally new and novel approach for the creation of programmable cell therapies. So our intent is to use and develop this platform to both develop our own in-house programs, but also to partner programs with companies who see value in what we are doing. So we've got a uniquely powerful and proprietary gene silencing technology. And the one reason I'm really excited about our technology is because we've spent so many decades now trying to construct and create molecular cassettes to deliver genes into cells and control those genes and regulate the production or the control of those genes in cells that's relied on taking promoters, different synthetic elements, plasmids, and embed those in the cell and hope that that molecular machinery we design in silico and then put in the cell, we hope that it works once that molecular construct hits the biology of the cell. And as we have learned, sometimes it does, but many times it doesn't. There's so much that conspires against us in terms of positional effect, epigenetic silencing effects, or immune response to some of those components that we put into the cell or deliver into the patient. The one thing that's significantly unique about the approach of Laverock and our platform is that we harness the cell's natural gene regulation mechanisms, and we recode those mechanisms and convert them into a gene silencing approach that is designed for our purpose. So rather than trying to add something into the cell, we're taking what the cell already has and editing it and changing it to our purpose. And this allows some really interesting things that I'll talk about in more detail, but for example, context-specific silencing, programmable silencing of genes, tunable, stable, and specific silencing. And by applying this platform and developing this platform, we believe that there's significant unmet medical need in novel therapeutics that we can develop. And we can develop advanced therapies which are more effective, that are safer, and more accessible. So who are we? So at a glance, so as I said, we've got our own platform. It's a proprietary gene silencing platform where we rewire the cell's intrinsic control mechanisms for our purpose. We're developing our own in-house program. So we've got programs that we're developing in both regen med and oncology. And we're looking at applications in both ex vivo and in vivo gene medicines. As I mentioned, we're open to partnerships, so we see a hugely powerful platform that could be used for multiple purposes, some of which we'll develop ourselves and others that we'll develop through partnerships. The company is now 2 years old. It's been built on the back of a very experienced management team. We've all been in the sector for a number of years with many company successes under our belt. And last year, we were able to complete our seed financing and raise $13.5 million with participation from Eli Lilly, Calculus, and several others. So that gives us fuel in our tank to continue to expand and develop the platform. So the platform, as I've said, what we're doing is harnessing the cell's own gene control systems to develop programmable advanced therapies, and advanced therapies that can then respond in specific cellular conditions or in disease states. So here's a cartoon of how we actually achieve that, just to give you an overview. So in essence, what we're acknowledging is that each cell in our body does a fantastic job at actually controlling its own orchestration of its own gene expression to give us a differentiation of the different cell types in the body. That's achieved through many non-coding elements within the DNA. And one of those key elements is the use of microRNAs that are naturally produced by the cell and used to silence or activate certain genes in response to triggers at different times and in different places. So what we're doing is we've got a bioinformatic capability that helps us to analyze cells and cells under specific conditions to understand the library and the complex orchestration of these naturally occurring microRNAs. What we then do is match those naturally occurring microRNAs in terms of their structure and function and identify a new target that we want to silence, identify a novel trigger sequence that we match with a naturally occurring microRNA, and then at the DNA level, we edit that naturally occurring microRNA and convert it now into essentially what is our programmed microRNA against a new target. So all of the natural control mechanisms that dictate when and how strongly and under what conditions that natural microRNA would have been produced is now taken over and used by our artificial engineered microRNA against a new target. And so we redirect that new target to give tunable expression without having to do significant manipulation or engineering of that particular cell. And we can use those microRNAs then that we design to either silence an endogenous gene or to silence an exogenous target, for example, a virus that's trying to come in and replicate within that cell. So it's a uniquely powerful approach, and it has some really interesting, unique features. In terms of comparison, it's probably a combination, most easily described as a combination between genome editing and gene silencing. So in genome editing, we can basically go in and knock out a gene. It's done at the DNA level, so it's stable and it's specific, but it's a binary choice. It's either there or not there, so it's not tunable, and it's certainly not programmable. With gene silencing, through dosing regimens, there's a possibility to achieve tunability, but it's not naturally programmable, and it's certainly not stable, and it's not specific, because the dosing level that those siRNAs delivered end up having off-target effect. Whereas with our platform, what we're able to do is achieve gene silencing, which is programmable, stable, tunable, and specific. And we have data that we've generated since we formed 2 years ago to demonstrate biologically each of these features. So in the top left, you can see stability. So this is where we've gone in and edited a novel microRNA trigger sequence into a pre-existing microRNA within a cell, taken that cell through cloning steps, expanded that up through multiple populations, and you can still see an incredibly consistent level of silencing of that new target gene. On the top right-hand side, you can see that through our screening, we're able to identify combinations of trigger and microRNA that give tunable silencing. So we can achieve silencing either anything from 10% silencing through in excess of 90%, essentially knockout of gene in terms of level. We can identify that in a screening platform, and then when we go in and make those edits within a cell, that level of tunable silencing is directly replicated within the edited cell. And a couple of graphs there show both stem cell editing, where we've knocked down a gene to around 90 to 95%, but also in a donor-derived T cell population, where again we've been able to show an edited cell line with 95 plus silencing. On the left-hand side, at the bottom, we've identified the question of, well, you've reprogrammed something naturally occurring within the cell, so do you have a loss of function? And how specific is that recode? Do you have any gain of function as a result of that? Now, in our bioinformatic algorithms, what we do is actually identify redundancy within families of microRNAs, so we can confidently make an edit to a naturally occurring microRNA, knowing that there will be no loss of function because there are other complementary microRNAs that have that same function. And when we've then analyzed the cells that we have edited and done a massive transcriptomic analysis of those cells, then what we've been able to show is that only our target gene has been silenced in our edited cell lines. So we know that there is good control over specificity with no gain or loss of function from those edits. And then the fourth key feature then is the programmability aspect. So here, what we do is we identify microRNAs that are expressed within a cell under specific conditions, or only within specific cell types and not others, and edit those so that our silencing function is only turned on when that cell exists under those specific conditions. And the example here is a iPSC line that we have edited, and edited a silencing microRNA into that, but knowing that that microRNA should only be expressed when that iPSC cell becomes differentiated into a monocyte or a macrophage. And the data supports that that actually is what happens. So the gene we're looking to silence here is only silenced when those cells become differentiated. And we're now following up, looking at doing that in the context of a tumor microenvironment. So huge benefits from this platform. As I said, it is hugely powerful. So from the right-hand side here, what we're doing is developing the platform as a way of creating new allogeneic approaches. So here we're able to show that by doing a partial silencing, so a single edit of a naturally occurring microRNA, to convert that into a microRNA now that targets in a tunable manner beta-2 microglobulin, when we see just that partial silencing of the B2M gene, then in an NK killing assay, we're able to show that we have less killing of our edited line than the B2M knockout. So we're using this now to create programmable hypoimmunogenic cell lines. We've also been able to show that we can do multiplexing of this and target multiple genes within pathways, again, opening up new disease indications that we can tackle. So unique features that open up a range of applications. So as I said, we're looking specifically at conditionally hypoimmunogenic cell creation. We're also looking at using the platform to develop edit cells to pre-program their differentiation using the timing of specific microRNAs to silence specific transcription factors during a cell's development. We're also applying the technology to achieve conditional tissue responsive indications. So for example, program immune effector cells to be activated specifically in the tumor microenvironment. And we're also looking at creating cell therapies which have built-in virus resistance. So if you go into a patient that has a significant viral load already, you can make those transplanted cells resistant to infection by that particular virus. So the programs we're developing ourselves internally are broad spread at this stage because we're still using these as a way of developing and validating the platform. So we are working on iPS-derived pancreatic islet cells, and here we're focusing on the feature of hypoimmunogenicity, but programmed hypoimmunogenicity. So the intent here is that the cells, when they differentiate into beta cells, are hypoimmunogenic, but precursor cells or any other contaminating cells as a result of that differentiation protocol are not hypoimmunogenic. So they would be cleared by the body, or if any cells de-differentiated, they would be cleared. We're also working on programmed T cells, so T cells which are programmed so that checkpoint inhibition occurs only when that T cell is present in the tumor microenvironment. And if that T cell then moves and leaves the tumor microenvironment, that checkpoint inhibition would be lifted. And again, this is both a key efficacy but also a safety feature. We're also working on macrophage biology, and so we're developing macrophages which are programmed to be driven and polarized to a pro-inflammatory state, again, only within the context of a microenvironment. So rather than being recruited into the tumor and converted into tumor-associated, the TAMS macrophage phenotype, they would actually be pre-programmed to be polarized to be pro-inflammatory, but if they then left that environment, that trigger would be lost and they would no longer be pro-inflammatory. So again, both an efficacy and a safety feature of the technology there. So I mentioned we've got a world-class team in the organization. We're all experienced and have been in the biotech sector for a number of years with a number of successes under our belt. We're still recruiting, so watch our LinkedIn space for jobs that we're still hiring for. So in summary, we have a platform I'm really excited about. It's uniquely powerful for the creation of programmable advanced therapies. We have a number of internal programs we're developing to exemplify the technology. We're going into in vivo studies this year, and we'll have more data by the end of the year on that. But we're actively exploring collaboration opportunities as well, because there's many more things this platform could be used for than we can pursue ourselves. And we have the leadership team and the finances behind us to drive our success. Thank you.